My name is Peter Logan, Chief Coach of the DHPC, and I'm going to be taking this pilot exam session on meteorology. What we're going to go through is take the big view of the Earth and then step down to the smaller types of features. So we're going to start off with Coriolis effects and pressure systems, and the jet stream, how that breaks down into the structure of the atmosphere. And then we're going to go through smaller scale things like examining the layers of the atmosphere, how they give rise to soaring lift that we can make use of, and how we can see that in forecasts through examining skew-t diagrams, synoptic charts, and understanding the lapse rate, how air is forced up. And then some of the minor sort of flying conditions that you're likely to encounter, valley breezes, and also sea breezes as well. So why is this part, meteorology specifically, in the, excuse me a second, I'll edit this part out.
I don't get the flash.
No, that's for a different camera feed. I'm making a rod for my own back here because I'm just going to have to edit this out. Anyway, so, you know, why is the meteorology section in the pilot exam? Because we don't necessarily need to know it for the Civil Aviation Authority. But we do have to know it because the BHPA mandates it, and we kind of presume that the Civil Aviation Authority would want them to do that. It's a responsible thing to do. But more importantly is the second reason, because we've got to be able to fend for ourselves. So in two places this is important. On the night before, the morning, the day of going out, it's important to be able to know what the day is going to deliver to you, not to maximise your cross-country distance, mainly for safety. When do you want to be landing by? When do you think it's going to blow out on the hill? Forecasts and meteorology will tell you that. But also for safety factors in the air as well. So an understanding of how air flows, what likely valley winds you're going to encounter, how those are affected by the day and weather types is important in this country, even more so flying abroad, particularly in the Alps. So I said we'd start big. We're starting with a planet. And we've got a planet that rotates. And if you've ever sort of thought about a sphere rotating, it's a lot fatter in the middle. So it's going to be going round a lot faster. About 1,000 miles an hour. But by the time you've got to Scotland, it's only going around at about 600 miles an hour. And what that leads to is this Coriolis effect. Because if you think you're standing on the edge of this sphere and you throw a ball, that ball, I'm going to throw it a long way, that ball is actually going to be decoupled from the Earth's surface the moment you let go of it. Yet the Earth, as it moves north, is going to become smaller, which is why it appears to turn right. The ball thinks it's going in a straight line. It is going in a straight line in its own frame of reference. But because it's decoupled from the Earth, that initial momentum that you gave it, the going north force and the turning round force, actually means that it starts to travel and move to the right as you go north. Easy?
Silly question.
Go.
So, it moves. It doesn't go back from where the Earth is. It moves with the Earth because it's still being carried by the Earth's gravity.
So it moves with the Earth's gravity. So
yeah. Right, so it moves with the Earth's gravity, but because the Earth moves, that's why it goes in the
exactly, yeah. So that ball, as it moves northwards, it's moving to a band of the Earth that's actually travelling slowly.
Yeah.
So it would tend to go right. And of course, you know, because this is all in the same frame, it's in the frame of reference of the thrower of the ball, the thrower of the oxygen molecule. That person will also be there. Let me show you on here. That you will have travelled around there as the ball's turned up there. Yeah. And of course, the corollary of that is throwing it south. It will also turn right, but that appears to go in a different direction when viewed from above. And what then tends to happen is that when you get flows of air, those flows of air also obey this Coriolis force. So high pressures go up. Let's get this right. High pressures involve air at height traveling down to compress the air near the surface. And of course, as you go down and you turn right, sorry for people on the audio stream, you're not going to see this. You're going to spin down right along the helter-skelter. Now, low pressure, conversely, you're going to spin up right.
Up left.
Up left. Yeah, good. And then imprint on that the fact that the sun's heating the Earth, and you're now getting these cells that are forming. So more sun at the equator gives you almost constantly rising air between the Tropic of Capricorn and Cancer. And that then sets up circular tunnels, if you will, that then have sinking areas at about 30 degrees. That's, funnily enough, where you get the big desert areas of the world, because the air is constantly high pressure, constantly sinking. It's very hard to form clouds. It gets a lot of sun all the time and very little rain relief, which is why these belts tend to be sort of desertified or at least fairly arid. And then these cells continue up to the poles. Of course, all of these cells, with the rising air and with the falling air, are rotating themselves to the right with the Coriolis force. And what then gives us are these different general flows of wind. And these translate to being the trade winds or the doldrums, where you expect very little wind at all. And here's a view as though you're looking through the atmosphere. All of this rising and falling is happening within the troposphere. Which changes height. So because there's much more vertical circulation, there's more sun activity near the equator, the troposphere is actually a bit higher. And you can see Britain's nicely positioned within the top end of the feral cell. And what you get with these convergences and divergences are places where jet streams set up. So there's an equatorial jet stream, and we're in a polar jet stream. And that's why Britain gets so much weather. We have a jet stream at about our latitude moving up and down that directs lots and lots of different weather systems towards us. A little bit more on the troposphere and stratosphere, and also the boundary layer here. So the troposphere is bounded by this distinct layer called the tropopause. And what happens is that all of the vertical mixing tends to be constrained to the troposphere. And above that, as you move into the stratosphere, you lose all of the water in the atmosphere. And you also get a very distinct change in the temperature gradient, which means it's fairly easy to tell troposphere from stratosphere. That temperature gradient actually starts rising. So as we move into the stratosphere, what we've had from ground going upwards is temperature disappearing or dropping with height. It actually starts increasing with height at the stratosphere, and that's caused by the ozone layer. So the ozone layer absorbs UV. In absorbing that UV, it warms up, which gives us a massive inversion here on the stratosphere, which is why we tend to see all of our weather systems contained within the troposphere. The boundary layer itself, so that you can see that there's large scale vertical movement here.
That may also why the sky is blue. That also be why the sky is blue.
I believe the sky is blue because both nitrogen and particularly oxygen, when they re-radiate, photons radiate in the blue more strongly.
I thought it was particles.
Yeah.
Light comes off particles, because if it's an inversion, there's going to be particles then trapped.
Yes, that tends to be very red in my experience. Yeah. Yeah, an inverted sunset at night time would give you, quite a red or orange sunset at least anyway. What we've also got as well, probably a little bit more important for forecasting what the day soaring is going to be like, is the boundary layer. Now, this is the first maybe 5,000 to 10,000 feet of the air that you can expect to be vertically fully mixed within a day time scale. So that becomes very important for modeling the day-to-day soaring conditions, the boundary layer, how much vertical mixing, where your local low-down inversions are, whereas the troposphere is the large-scale mixing for weather systems as a whole. And there we go, polar jet and subtropical jet. So that jet stream moving from west to east tends to wave about, and there tends to be an oscillation of about 6 or 7 waves going around the whole globe, but it can change. It moves north during the summer and south during the winter. I changed that this morning. I'm not sure, David put these slides together. It does not appear to save the changes that I make. And like I say, you can have a number of wavelengths as the jet stream, the polar jet stream goes around the globe. Meridional is wavier, even though the diagram doesn't show it. Zonal is smoother. I will fix this in the video edit come hell or high water. And it's at the inflection points, the turning points of the jet stream, that you actually get the weather systems that come across. The lows, as the jet stream bottoms out to the south and starts moving back north, and the highs nicely tucked in to, I guess, the armpit of the sine waves. Why is that, Clive? Yes, we're going to find out. And they tend to move, lows move northeast, highs moving southeast. And the reason for that is that you've got the jet stream not only having a wavelength as it flows around, it also has convergence and divergence, so it gets fatter and thinner. And as it does get fatter and thinner, then that affects the pressure systems below it. So in moving towards this thin layer here, we've got pressure within this constrained flow of the jet stream. So that pressure tends to lead to air descending, whereas this divergence here leads to the ability of the jet stream, I guess, to suck in or entrain air from lower down. And then that's got to be filled in, and that affects all the way down to the surface. So what you tend to get is just at the bottom trough, these lows start to form, and for us that's lows that are forming out in the Atlantic. And as these lows are forming, they're subject, those flows up into the atmosphere are subject to the Coriolis force. And in rotating, they start to entrain air from the other side. Hence, we get this warm air, this Atlantic air that's not been affected by the colder air above it, being entrained into this colder air system. I mean, these are, 500, 1,000 miles. So as you get the ability, this warm air moving in, it's moving in some hundreds, quite a number of hundreds of miles. Hence, you are likely to get a temperature difference on that scale. And that forms our two classic fronts, our warm front, followed by a cold front. And we've had plenty of that action over the last 2 weeks. This is what it looks like when it hits the UK. And you can see that we've got a classic warm front and a classic cold front. We have even something to watch out for. You can see it in the pressure lines around here. But there's a little veering in the wind after the passage of the warm front. And you can see here that after the passage of the cold front, again, you get a characteristic veering of the wind direction. Veering as in going around the compass clockwise as opposed to backing anti-clockwise. So these are your synoptic charts, otherwise occasionally referred to as NSLP, means sea level pressure. And what you've also got at the top end of this low, very common, is the cold front has caught up with the warm front and has led to an occlusion. We'll go into a little bit more detail on occlusions a little later. It's well worth knowing that the reason these occlusions occur is that the warm front moves across the ground more slowly than the cold front. So the cold front is constantly catching it up, catching the warm front up, and actually lifting that front up from the surface of the Earth.
A warm front, does a warm front ever catch up with cold?
Not that I'm aware of. And you can see also that the warm front is generally what hits the UK first. As these low pressures move in, we see cloud behaviour associated with the warm front, then followed by the cold front. Incidentally, and this is an exam question, you get this Bayes balance law as an offshoot of the way that lows and highs rotate. And very easy to remember, when you stand with the back to the wind, your back to the wind, the lowest to your left, the highest to the right. But I thought this was a really useful place to put all of the different terms that kind of mean the same thing. So anticyclones are high pressures, they're clockwise, and also that direction of air on the surface is veering. Lows are cyclones, they're anti-clockwise, looked from above, and they're backing. So this is kind of what a front looks like. You'll see that the actual angles have been exaggerated a little bit. What you can expect for a warm front is that its actual gradient is 1 in 100, 1 in 300, 1 in 400. They're shallow. A cold front, hey David, cold front is actually quite steep. Now this is completely oversteepened. Both sets of angles have been oversteepened so we can fit something meaningful on this diagram. But cold fronts tend to be 1 in 10s, high 10s to 1 in 100. It depends if they're an ana or a kata front as to how steep they are. But rest assured, a warm front is very much less steep than a cold front.
That's showing that's actually showing them. So the warm front there is going right. Is that correct?
Yeah. Thanks, Peter.
Right?
Yeah, flow from the left to the right here.
But the cold front there is going left.
No, it's not. Both of them are moving right.
Both are moving right.
The arrows are just showing the distance.
Yeah, so what we're looking here at is the salmon coloured arrows are actually starting to give you a variance in the wind from what you'd expect compared to the synoptic charts. Okay, so the synoptic charts will give you the flow of the wind around the isobars. And that's known as geostrophic flow. But here, associated with the front, you get something called ageostrophic flow. So it's flow of wind not associated with the pressure front itself. It's flow of wind associated with the approach of the front itself. And you can see here that with the, the bullying cold front on the left-hand side, well, it's pushing air in front of it. That has two effects. It's pushing air up the warm front, way ahead of it. But it's also pushing air up directly in front of it, up and over, leading to Cunans, yeah. But yeah, leading to rising air, not directly caused by the pressure system wind flow. And in fact, quite often what happens with cold fronts is that they do oversteepen near the surface because they're subject to friction on the surface. Mountain ranges get in their way, valleys get in their way, and trees slow the flow down as well. So this might be tens of thousands of feet high. But of course, the bottom few thousand feet, the bottom 3,000 or 4,000 feet, may lead to the slowing of this cold front for a while because of friction on the ground.
Can I ask a question?
Yeah.
Okay, so a couple of weeks back, I was in Northumberland walking, and the top clouds, cirrus clouds, were stationary. But below that were outer cubes moving at considerable speed. I'm put myself out there, is that because the cold front actually had met the warm front, the warm air, and therefore the warm air was trapped at the top, but the cold front moved through underneath it, or what?
Do you remember what direction?
It was coming from the west.
It was coming from the west. So the outer cubes were moving from the west.
Yeah, that's understood.
Yeah, but there was cirrus stuck up there.
Absolutely, yeah.
Okay, so I mean, it's quite possible for wind to vary with height. Yes, more common for wind to be much stronger with height.
Yeah.
So there's a couple of possibilities. It could well be that just because of the sort of foreshortening is the right word, but just because you were closer to the altitude, it was easier to see the movement on that compared to the cirrus. So the cirrus might have been moving relatively quickly, but looked stationary compared to what was moving straight above you, at 6,000 to 10,000 foot above your head. What it also could have been is that cirrus could have been associated with a previous front, and or up at height, the dew point could be quite close to the environmental lapse rate. And or you may have wavy flow that then allows cirrus to be present whilst this outer cube comes in as the sort of approaching cloud on the warm front. So any one of a number of possibilities. Yeah.
It's really quite dramatic.
Yeah. So being able to pull the tephigram, the skew-t diagram from Dave, would help us explain that actually.
Right. And
we'll go into that a little bit later. So what we do get with these ageostrophic flows of air being generally forced upwards on the back side of the warm front, the front side of the cold front is the formation of cloud, and that quite often means rain. Don't forget, a warm front has had the energy, has the air in it that has the energy to absorb a little bit more water from the sea or the ground that it's passing over. So you do tend to get higher humidities or higher relative humidity in air that's associated with being in between a warm and a cold front.
Is that what's called a warm sector?
So this is the warm sector in between what's usually called the cool. So the warm sector just doesn't have the energy to bully this cool sector out of the way. It's not as dense to start off with. So naturally, as it's moving and rotating due to the Coriolis forces, as it's rotating, it's forced up above the cooler air that it's trying to shove out of the way. No such problem for the cold front. That just bulldozes everything in front of it, leading to kind of drizzly sort of conditions. If you do get any rain associated with a warm front, but much more dynamic cloud building, occasionally thunderstorms, cumulonimbs, squall lines associated with the passage of a cold front. And here we're just concentrating a little bit more on this ageostrophic flow, where even within the front itself, there's circulation that reinforces the convergence of the cold front and the warm sector on this left-hand side, and also cool air.
So what that other slide was showing was why the cold front tends to move faster than the warm front. So if you move forward,
Yes.
forward there, because the ageostrophic flow supports a cold front. See, it's kind of pushing the warm front forward. That's the blue line on the cold front. Whereas the ageostrophic flow on the warm front tends to counteract the movement of the front, pushes against it. So you find the cold front is moving faster. Cold fronts generally move faster than warm fronts.
About 20 miles an hour.
Yeah, and this is
Usually a bit more, 20 to 30 for a cold front, 10 to 20-ish, 10 to 15 usually for a warm front.
Yes.
So they're always being chased down.
So again, weather associated with a cold front would be drizzle.
Generally, yeah.
Yes.
The lighter rain. But again, you know, we've got this amplification of these two different speeds of the fronts. If you notice here, when you have rain falling on the warm front, that's falling through already cold air. Okay. But here, there's a big difference. This rain is falling through already warm air. And the fact that it's already warm further cools this air down in front of the approaching cold front, which allows the cold front to progress more. Again, it's another ageostrophic wind flow. Not caused by the pressure of the front, but caused by the cooling due to cooling of the atmosphere due to evaporation. And those are another, well, I guess this is a summation of this airflow that you get at various fronts. So you see here that the ageostrophic flow on the warm front opposes its motion on the ground, whereas the ageostrophic flow of the cold front adds to its motion on the ground. And here we get the types of cloud associated with each of the fronts. So this is where we get our phrases: red sky at night, shepherd's delight, red sky in the morning, shepherd's warn. If we've got red sky at night, we've got the sun showing on either the back of a warm front, because the sun's setting in the west, so you're looking at the red sky being in the east. So it's lighting up that past warm front, or it's lighting up the back of the cold front. Red sky in the morning shows you what's coming. Lighting up this warm front from below. If you can imagine the sun rising here, it's obviously lighting up the bottom side of this cloud in the morning. So because warm fronts are so shallow, sometimes they take days to come in, and you can see the cirrus, sometimes starting with very light grey sundogs almost, and then forming things like a mackerel sky, the parallel lines of cirrus ice crystal cloud, and then forming the alto stratus. Finally, if it's an active warm front, nimbostratus. Nimbo just meaning rain. Period of relative calm before the cold front comes in, and the cold front is usually marked by an active weather front, quite often raining in the UK, certainly raining this time of year, and always marked by very heaped clouds, meaning lots of convection. And then after the passage of the cold front, light, puffy cumulus, very clean blue skies. Those cumulus, depending on the relative humidity of the air, the temperature of the ground, what the lapse rate is, those cumulus themselves might be tall enough to form big showers themselves.
Cumulonimbus at the front of a cup, on the leading edge of the cold front.
Not always, but very often, quite often. I've never counted it myself, but cumulonimbus is generally characterized by a cloud that will go all the way to the top of the troposphere, which could be 25,000 foot in the UK. And certainly with the passage of a cold front, you don't need clouds that high in the UK to start raining. Clouds that are just a few thousand feet thick quite easily rain if the relative humidity is high enough and the conditions are right. Definitely an exam question.
Yes, certainly. I was just going over again the different weathers that are coming with it. So
yeah,
you've got the cold front, you've got heat clouds coming in with the cold front.
Yes.
You've got three things here. You've got a warm sector in between the cold front and the warm front.
Yeah.
So you've got nimbostratus there.
Yeah.
At the beginning of the warm sector, and then at the beginning of the warm front we have rain again.
Not necessarily. Not necessarily.
Just cirrus. So what do we see? Is that what we see at the beginning of a warm front? Cirrus.
Generally, yes. Yeah.
Right.
Not always.
But
commonly, yeah. And there are different reasons for that. You've got different levels of activity of a front, different depths of pressure, but also different temperature gradients at height, which lead to less or more active frontal systems associated with a low. But generally, this rain here may not even reach the ground. So quite often you can see flat cloud off in the distance, and it looks to be raining, but it never reaches the ground.
This is a name for that, isn't
Is it Virgo?
Verge. I think it's-
And what's happening there is that in this cool air, the relative humidity is low enough to evaporate all the droplets before they hit the ground.
Is that something to watch out for us paragliders? Flying and being rained on unexpectedly, basically.
Yeah. I mean, it's not uncommon.
I would
To
actually
feel-
rain on unexpectedly. I've always expected it.
Yes.
If I was going to be rained on, I knew it was coming.
Yes.
Yeah.
Rain that
There's
in
not
other
some
words,
something appear out of nowhere.
Yes.
With a decent pulling cumulus cloud, it's not completely unexpected that you'd feel a bit of rain at cloud base. Even though there's no chance of that hitting the ground at all.
Yes. There could be something to watch out for.
Yeah, to be honest, you can see rain, active rain, from a cloud that you're thermally up next to or near to.
Yes.
So you can see it to avoid it. So you just generally tend to occasionally feel the odd spot. So one reason for being in an active or non-active part of a weather front is actually how deep that low pressure is itself. Another one is anafronts, which are much more active, I guess, where air is able to rise to the full extent of the tropopause. And that's because with the environmental lapse rate of the air columns through this approaching front, you don't really have much in the way of an inversion that would stop those active convection currents rising up to the full extent, going past the freezing point, forming hail, snow, and rain. Contrast that with a kata front, where you've got descending air at height, which gives you this thing called a subsidence inversion. That tends to put the cap on the worst excesses of cloud behaviour at fronts. You still might get wet, but probably without the lightning. And the way that they look on skew-ts, now we're going to cover skew-ts in some detail probably after the bio break, but the way they look on skew-ts here, or the active type of front, you might just be looking here at, a small inversion, maybe at the 1,000 to 2,000 meter mark, 3,000 to 6,000 foot. It's showing that. However, at about the same height, that kata front is showing you this wide divergence of temperature with height, increase of temperature with height, the divergence of the dew point from the environmental lapse rate here. And that's indicative of the descending air drying out the air at height and putting a cap on any convective activity. So I said we'd move into occluded fronts a little bit. And effectively, your occluded front is that warm sector lofted up, because what's happened is that the colder, denser air of the cold front has caught up with the cool air left over from the passage in front of it, passage of the previous set of weather fronts in front of it. That warm air gets lofted up again because air is being forced upwards at some meters a second occasionally, you're going to get the possibility of rain. So an occluded front is no promise of good weather. Having kind of muggy grey conditions because of an occlusion is quite often very common. Typically, the cold occlusion is what we're getting in a low pressure. I'm going to go over to my esteemed colleague David. The warm occlusion, is that from the weaker fronts associated with a high pressure system?
That I don't know. I think I don't know what pressure system creates one or the other. Just when you have cold air meeting cold air, there's still going to be a temperature difference between the two bodies of air. So one of them is going to be colder than the other. If the one catching up is colder than the one on the front, it's cold occlusion. If the one catching up is cool, but the one that catches up is cold, it's a cold occlusion. It's a warm. The weather's the same either way. It just pushes the warm air up and it all spreads out the rain. So,
Get your umbrella.
but I don't know what causes one or the other.
And all of this is given to us in a synoptic chart.
It was a quiz slide.
So you will get this on the exam. You will have to tell the weather from various points on a synoptic chart. So should we start with A? Who would like to tell me something about what's happening at point A on the map?
So it's a warm front, we're at a warm front.
We're at a warm front. What type of conditions would you expect at the warm front? At that particular warm front? Where's the wind from?
From the south. West.
Yeah.
We call it an angle, isn't it?
What's
Yes, so from the southwest.
yeah? What kind of cloud would you be looking at there?
Cirrus and alto stratus.
Also, this point here marks where the warm front is on the surface.
Nimbo stratus and light rain.
Sounds good to me. Yeah. The Icelanders deserve it. B.
We're in a low pressure there. It's a cold front.
Yeah.
High winds.
High winds. Yeah. What tells you that?
Close isobars.
Close isobars. Good. Yeah.
What kind of front is that be?
I thought cold front.
It's included.
So, sorry, yeah. Yes, it is included. Yeah.
So the typical weather at an occlusion.
Nimbo stratus and rain.
Good.
Yeah. Which go for separate answer, isn't it?
Yes.
I'm gonna try something.
C.
That's the cold front.
Yep. And weather.
Possible.
Heavy rain.
Yeah.
Yeah. Change of wind direction.
Yes, from the northwest.
Yeah. It's actually a little bit of a funny one, is that? I mean, if you look at, now I'm looking at it, at this around, you know, the sort of Moscow-y, or Lithuania, I guess we're in Lithuania, and although they're up there, aren't they? Yeah. Up here, you're looking at that traditional sort of veering of the wind, but down here with this cold front, this same cold front, you know, as you're stood on the ground and the front maybe passes over you, the wind backs. But that could be much more to do with these, you know, the very slack isobars from the high pressure that it's pushing out of the way there. So it's not always that you're going to get a veering of the wind as the front passes.
So it's quite a good example of how it's catching up the warm front. Yeah.
Yes, absolutely. Yeah. Yeah, you can see here you can really imagine that this is off spiraling into the upper atmosphere as it goes upwards around the Baltic there. D.
High winds again, low pressure.
And the wind direction.
From the northwest.
Yeah, from the north. Yeah, yeah.
You've got to go like that way, don't we? We're used to
Yeah.
the British
I mean,
Islands in a northerly sort of
D.
thing rather than.
Yeah, don't.
What would wind on the ground be? That's a low, isn't it? That it's spinning around?
That's a low. It's spinning round.
Yes, yes. Well, it's changed. The ice so it's changing from north to northwest, I would say.
Yeah, well, west, isn't it? It's
Yes.
spiraling in. And for low pressure, it spirals.
Yeah, on the isobars, it's coming roughly from west. But
Well, it's
on
coming from
ground-
the left of the picture, but the left of the picture is northwest. If you look at the British, I'm looking at the British
Yeah.
Isles, and it's north is in the top left-hand corner.
So you can see the line of
Yeah.
longitude here. Yeah.
Yes. So yes. Yeah. Yeah. North is top left corner, not top of the map, roughly.
Keep in mind on the ground, the wind isn't parallel with the isobars. It would be
Oh yes, there is a degree.
leaning in towards the low and
15 degrees.
about 15
15
About
degrees.
15
Yeah.
degrees. Yeah, it's a good point.
So on the ground, because you will be asked things like that as well. What's
Yes.
the wind direction on the ground based on the isobars? So
So hold on. So would the direction then at D then be more in towards the low?
about 15, 20 degrees.
Yeah, so it would be northwest flow.
And the high pressure would be spiraling.
The other way, so it's
High pressure spirals out. Yeah.
Yes.
Yeah.
Right. That's one to remember. Yes.
You know,
ground it's
only a
inward,
little.
and on the high pressure, it's outward.
Yeah.
Where the actual.
But if you imagine it at the centre of each low pressure, there's a big Hoover nozzle. Yeah, so as soon as you're crossing these mountain ranges in Scandinavia for point D,
Yes.
that's of course going to flow that geostrophic flow down, and of course you slow down, or you slower flow down. It's going to leave it open to other factors, like the fact that this low is actually lofting air up. So it's going to suck the air in as it slows down. And in fact, I forget the exact height that synoptic charts give the isobars for.
2,000 feet,
Is it 2,000
I
feet?
think.
Yeah.
So that's the wind at 2,000 feet.
But yeah, they're giving you the wind flow at 2,000 feet, but of course the pressure reading at mean sea level. Point E. What's the weather going to be like at point E?
But we're in a high pressure there.
It's really
Yeah.
lovely.
So,
Time to get the shorts out. the
yeah.
t-shirt,
That's
On the
right.
beach.
It is a cold front, but it's a way off. So yes, balmy weather.
Can you see that? It's in January.
Yes, but still sunshine. Yeah.
It'll be all right. You'd still rather be there.
Yes.
And point F. Good old Blighty.
Well,
So it's January.
Yes, but we're in a high pressure though,
Yeah.
so fair weather.
Fair weather.
Yeah, the front's moved through, so there could be some residual cumulus.
There could be. But don't forget, we're dominated by high at the moment. So there would be thermic activity, and I think there'll be a lot of sun on the ground because of this high, which is going to tend to suppress cloud. But I think the conditions that we've got here, this weakened cold front south of F that we can see here, will have left us with some drier air.
I've seen that on. I've
Blue.
seen that before.
Yeah,
So is that triangles and plus signs?
yeah. So this is just a faded cold front.
Right.
And so that's going to have left us, certainly overnight, with cooler, dry, cloudless air. So I think Britain will be looking at one of those classic winter,
Yes.
icy blue, clear days. With, quite a nice sunset, sunrise, because of the inversion that we'll have got. Maybe a little bit of cloud associated with this trough to the north along the North Sea.
Would that be any good for flying? Or is it too light a wind? Too light a wind for flying on F?
On F, I think that would be fun. Yeah. So one rule of thumb that an old instructor taught me was when there are more than 4 isobars, and these are isobars that are 4 millibars apart, 400 pascals apart. When there are more than 4 of those crossing the UK in a north to south direction, it's going to be too windy to paraglide. So if you imagine that gap there between 1028 and 1032, this gap here,
Yes.
you maybe only get 3 of those across the UK. So I think that would be quite a nice day to fly.
Yes.
And wind direction from
This is an F for flying.
From north. As you're looking at north.
Yeah. Trestle Ward.
Yeah. Which way the wind's going there? We're going round in west direction.
Yeah, so they'll be
Northwest, isn't it?
Yeah, they'll be moving out of the high pressure a little bit, so crossing the lines on the surface. So north-northwest. Yeah. We'll be going to Sutton and Cowling Pinnacles.
Going for a set record.
And of course, all of these different directions for wind to be approaching the UK translates to different types of air mass that you can typify.
Yes.
And certainly what we would have been getting there is either Arctic maritime. I'll publish all of these. Yeah.
That's the right one.
Certainly Arctic maritime air mass or polar maritime air mass. And I think the wind flow from the last diagram would have been a little in between the both, but mainly we would have got Arctic maritime, which is cold air, it's dry air, because where the air's come from tells you a lot about how much water that air can hold.
Yes.
So if it's come from somewhere incredibly cold, you can't hold a lot of water. Okay, so if you can't hold a lot of water, cloud bases are going to be higher. Chances of rain are going to be a lot less. The clouds themselves are likely to be smaller in size and quite puffy as opposed to dense and towering. So generally in summer, Arctic maritime air mass, those northerlies, tend to give some brilliant cross-country flying conditions. So the day that a bunch of lads, not me, went from Model Ridge down to Stafford, 200k, was in Arctic maritime air mass. However, more typically for the Dales, we're getting those northwesterly flows. That gives us our classic flying conditions at Dodfell and Weatherfell. That's polar maritime or returning polar maritime. Generally, there's a lot more water vapor in the atmosphere, so it can be a lot cloudier. Rain is occasionally in the offing, so the odd shower is not unheard of. And then by the time we're moving around to thinking of flying, it's not Sutton Bank, Wing Bank, Kettlewell, or Stag's Fell, we're in either this returning polar maritime or tropical maritime air mass. So, quite often, we'll just discount quite a few southwesterly days because it's just not on. It's quite windy, a bit wet. But on the days when it does come together with either returning polar maritime or tropical maritime in those southwesterly flows, again, it can lead to pretty usable cross-country conditions.
That's our trade wind, really, don't it? Southwest.
Southwesterly is very common, yeah.
Yes.
Yeah. And then the two continental air masses, well, they're arriving at us having originated over land. So in summer, they can actually be quite warm, having been previously warmed by moving over the land. Doesn't always lead to the best of conditions, can be quite inverted. So our easterly flows, or southeasterly flows, can be quite a fight as cross-country flights go, in that they're sometimes weakened thermic activity or sometimes quite strong thermic activity, but always with some kind of inversion that we're fighting somewhere. And that can lead to some marked turbulence.
So the inversion is a buggy, so that's capping the height that you can.
Yeah, but an inversion will generally tend to break through the day. So you'll be bumping against it in thermic conditions before lunchtime, and then sometime after lunch you'll be able to get through it on a good day. Yeah. On any good cross-country day, you should be able to get through any inversion that's been set up by the cold air from the night before.
Yes.
It's not clear that you'd ever get through the inversion associated with the air mass at that height then. And in fact, I remember, one flight this year was actually in probably returning polar maritime air mass from the Bradwell Edge to Peterborough. Was actually, and it shouldn't have been that inverted given the direction, but it was mega inverted. In that you got to the height of the inversion, and you could see crystal clear sky above it, and you had this huge grey murk line that just faded out to the green of the ground below it. It was very marked. But typically, that kind of view is associated with this eastern air mass as we get all the pollution, but dust as well from the continent. And this tropical continental air mass is the one that does occasionally give us a dump of Sahara sand, which the weathermen always tell us about.
2018, we're getting a lot of that.
Yes, a few years back.
Yeah. I had a bunch of good southeasterly flights in 2018. Okay, so as we're moving in from looking at the globe with big weather systems and Coriolis forces and flows. We're looking at more local conditions, and as we move down through the troposphere, we get to the boundary layer and the surface. So heat causes air to rise. As that air rises, temperature drops, the surrounding pressure drops, and therefore the density drops. So that parcel of air actually gets bigger, but it also gets cooler. And that gives us several downstream effects. And what we get are, oh, absolutely, yeah. What we get are things called lapse rates. So a lapse rate is nothing more than a drop of some condition. Now, for us, that lapse rate is the temperature drop. So the temperature is lapsing. That's what we're talking about when we talk about the lapse rate for us. And then there are a few different kinds of lapse rates that we really care about, because, you know, we're talking about that parcel of air dropping in temperature as it gains height and becomes less dense. But that parcel of air had certain characteristics to begin with. And we have characteristics of all of the parcels of air as you go up through a column of atmosphere. So if you imagine on the top of your head, all the way to the top of the atmosphere, there's a lapse rate of atmospheric temperature. And that's what we call the environmental lapse rate. That's what the air does just as you sample it going up through the atmosphere. And that's how we find out what the environmental lapse rate is. We send a radio balloon, a radio sonde on a balloon up through the atmosphere to measure that. And that's done quite commonly from several locations in the UK every day, sometimes a few times a day. And then we've got those inherent characteristics of a parcel of air that we really care about, that give us a different lapse rate. And one's called the dry adiabatic lapse rate. Adiabatic meaning changing with pressure. Dry adiabatic lapse rate is where the humidity of the air is below 100%. So it's not cloud. So this is dry air that would obey the dry adiabatic lapse rate, changing temperature with height, if we just took it up in a plane.
Yes.
Saturated adiabatic lapse rate is the point or the temperature behavior with that piece of air, with that parcel of air. If its humidity has reached 100% and air is now condensing water out of it, water vapor is coming out of the air and forming droplets, because that parcel of air is now not at a temperature that would sustain the amount of water that is within it. So as you go up, as you go up through the atmosphere, the amount of water that will be held within the vapor phase, within that parcel of air, drops all the time. And so
it's cloud forming.
So yeah, so typically when we're caring about what happens with the saturated adiabatic lapse rate, try saying that after 2 points.
Yes.
We care about what's happening in cloud.
Yes.
Yeah. But not always. Saturated adiabatic lapse rate can also be used to typify how air changes in temperature in fog as well. We care about that less because we don't want to fly in fog. But the thing to bear in mind is that these lapse rates with a static column of air, this environmental lapse rate, dry and saturated, have different lapse rates associated with them. So taken as an average, an environmental lapse rate would be roughly a drop in 2 degrees Celsius every 1,000 feet, 300 meters or so. More for a dry adiabat, less for the saturated adiabat. And the reason that it is less for the saturated adiabat is that as that air condenses out of the, as that water condenses out of the atmosphere and turns into droplets, it gives up heat, it gives up some latent heat, and that cools the air as it goes. Warms the air as it goes. So you get less of a temperature drop with height.
Basically translates to the thermal actually picking up speed at cloud phase.
Yeah. Okay. So what I wanted to do was just to actually show you this. Because we'll have a little bit of backing music. Because of course, you know, what we know is that the air, when it does rise, does so in a cohesive way. And I just want you to bear in mind that this visualization of a thermal, effectively you're looking at a thermal, it just happens to be well animated on the side of a cumulonimbus cloud. But you can see that there's a lack of mixing, because even as it moves through the atmosphere with its environmental lapse rate, it's got a different density. And that difference in density causes it to have a very clear, marked boundary. It forms its own cohesive column, even though there's roll associated with it. There's actually not very much entrainment of the surrounding air. So these things do form quite self-sustaining convection currents. And of course, if we just go back, what I did want you to see just here was the widening at the top. You can see here that the diameter here, which is closest to us as we're looking up, is smaller than the diameter here, which is smaller than the diameter right at the top of the cloud there. And that, of course, is what you would expect from a parcel of air that's maybe been at 3,000 feet down at the bottom of frame, and now is at 8,000 feet at the top of the frame, or going much further on.
You see it in sped up like that. It gives you a real sense of the explosion that's going on inside these really big clouds. They look nice and benign, but the really big clouds are.
There's more joules in a Q-nin than a nuke.
Wow.
Okay, so now we've got a kind of a visualization of that. We can examine what happens with these lapse rates. So temperature along the bottom here, and you can see that 3 degrees drop per 1,000 feet gives you one particular gradient. That gradient changes after you reach this line called the dew point. So the dew point, which is shown much more sort of emphatically on the skew-t diagram. That dew point is the point at which your relative humidity reaches 100%. That rising air can hold no more water vapor and it has to condense. And therefore, you get, on a convective day, these lovely flat bottom clouds. And then also on a day where you might see sea air coming, or you're looking at air from two different sides of a mountain range, or even two different valleys, they can have two different relative humidities. That gives them two different dew points, and so you get two different cloud bases. And that's all to do with that point at which humidity reaches 100% and water condenses. And this gives you an idea of working out how to sort of typify the behavior of the atmosphere. I haven't seen any questions particularly on the states of the atmosphere, but it's well worth bearing in mind just for your own safety in being able to tell a day that is unstable, good, or absolutely unstable. Generally, you don't want to be flying in the afternoon near the big clouds. So in a stable atmosphere, you've got the environmental lapse rate always less than the dry adiabatic lapse rate. So that means that these parcels of air, if they're heated near the ground, they just don't want to rise. Unstable, your environmental lapse rate at some point is bigger than your dry adiabatic. So it can rise. Conditionally unstable. Okay, so you've got your environmental lapse rate. It's bigger than your DALR, but smaller than your saturated adiabatic lapse rate. What that means is that as soon as your packet of air reaches the cloud, it's going to hit the saturated adiabatic lapse rate and just die out. Absolutely unstable. Basically, that means Q-nims. Your environmental lapse rate, if it's all the way up the column of air, will just be going up to 30,000 feet. It is massively buoyant, and the only thing that will stop it is the tropopause and the inversion that you get at the tropopause 30,000 feet. And then another thing, exam question here, is working out from the information that you're given what the cloud base is going to be. So funnily enough, there's a little bit of a rule of thumb. So if you take the temperature difference between the temperature on the ground and the dew point on the ground, and then times that by 400 foot, then what you get is the height of cloud base. And sometimes you don't even need, on a good soaring day, you don't even need the temperature of the dew point on the ground. You just need the overnight temperature, the lowest temperature it got overnight, because you woke up this morning and there was some dew on the ground. So that gives you a rough rule of thumb, that if the Met Office or the BBC says it's a 25 Celsius day, and you know overnight it was pretty cold, and you saw some dew on the grass and it was 12 Celsius, then the difference between Yeah.
About 5,000 feet, 4,900.
I'm glad you just saved me the mental arithmetic. Yeah. So, you know, typically it would be the dew point at the ground as measured by one of those white boxes that cost several £1,000s. But generally on a good soaring day, the overnight low temperature will also give you that temperature difference to times by 400. Now, the reason that it goes up at 400 foot, which is not the dry adiabatic lapse rate, which is how many degrees C per 1,000 feet?
3.
3.
I'm sorry.
So you can't get 3 400s in 1,000, can you? You can get 2.5 in there. So what's also happening is that there's a 0. For every 1,000 foot, there's a 0.5 degrees C difference, and that's the dew point actually coming down as well, which is why you've got that 2.5 times then, or 2.5 times 400 in a 1,000 foot, because that parcel of air, as you loft it, it continually can hold less.
Yeah. Wind back slightly.
Yeah.
Sorry, because I was making a note of time speaking. With regards to the lapse rate, you then took the dry lapse rate, not the environmental lapse rate then, because you mentioned 3 degrees per 1,000.
Yeah, because
Not the environmental lapse rate, which is 2 degrees per 1,000. Why do you then mention the dry lapse rate?
well, because we're talking about cloud base.
Right, yeah.
So we're lofting this heated, buoyant parcel of air up to become a cloud.
Right.
And you'd have thought, that the dew point at height would be would follow the dry adiabatic lapse rate. But what's happening is that the capability of the atmosphere to have the same, to hold the same parcel of water decreases with height by about 0.5 degrees C per 1,000 foot.
I kind of get that
Yeah.
it kind of can change, but I don't understand why you're taking the dry lapse rate, not from standard environmental lapse rate.
Because, well, we're taking that dry adiabatic lapse rate because it is now this parcel of air at 23 Celsius has been given special treatment. It's been irradiated by the sun. It's now warmer. And so being warmer, it's more buoyant. And so it's going to follow that behavior, of a buoyant body and rise.
Okay.
And as it rises, it will be dropping in temperature at the dry adiabatic lapse rate.
So, but the air around it will be then.
At the environmental lapse rate,
Right.
yes.
So in other words, when it's in that body, that body of air that rises will cool more quickly than the air around it.
Yes,
Correct.
yeah.
Now I understand.
Yeah.
I'll forget that.
Yeah.
Well, if you think of it, the mass of air has the yellow, the environmental aspect for the speed it cools.
All around it.
But if you take a local body of air that's being heated by the sun, it cools quicker as it rises up. So eventually it'll get to a point where it's the same temperature as the air around it. Because it's cooling quicker.
Yeah.
And at that point, your temperature doesn't rise any further.
Yeah, because they're together then.
Yeah, and chances are it'll have passed the dew point at some point as it's rising and it'll form a cloud. On a blue day, what happens is the dew point is above that point. So in other words, you got this little bubble of air that's cooling at 3 degrees a second, rising up through an air mass that's cooling at 2 degrees a second. Eventually it meets.
Yes.
If the dew point is above it, you don't get any cloud. but the thermal stops rising.
Hmm.
Because the bubble is now at the same temperature the year round.
Right.
If the dew point is below that, you get a collapse.
To your point,
There you go.
this is the diagram that you need.
Oh, fucking hell.
Yeah,
Yeah, but also, if I knew my slide set.
yeah.
So this is your simple case where you heat that parcel of air to 5 Celsius more than the environmental air that it's been part of. And this is vastly sort of simplified because, you know, this environmental lapse rate, it's an assumption, it's an average.
What I would say, Pete, is it is vastly simplified, but this is what you're going to be asking exactly.
But you know, it's pretty much good enough for your own forecasting of the day's conditions. So yeah, you see that faster drop until you get to this point here, where both are at the same temperature and therefore at the same density, and therefore there's no buoyancy to loft that heated air much higher.
Right, okay, fine. So that's where the thermal stop, but there's no guarantee that that will be where cloud base is.
No, there's no guarantee. That's so.
So
It just happens to be, well, I mean, we've changed the height now, but we've added the complexity of a saturated adiabatic lapse rate brought on by the fact that the dry adiabat and the dew point, or the mixing ratio, or the SSH, you might see them on skew-ts. They actually intersect here. So where a dry adiabat and the dew point line intersect, that's where, you know, you're getting the indication that the relative humidity is getting higher and higher and higher to 100%, and therefore cloud starts to form. And then after that, any lift within that cloud, and there's heat being liberated at that point, so there's no reason for the lift not to continue if there's no inversion. That then cools at the saturated air diabat. And again, you can see here that there's a divergence between the environmental lapse rate and the saturated adiabat. That means one thing: if these are diverging, then that buoyancy is going to be diverging as well. This cloud is going to want to go gangbusters until the actual air temperature gets in the way, and we hit here an inversion, or another way of thinking about it, temperature rise. Temperature goes up with altitude, which is against the environmental lapse rate that you commonly assume through the atmosphere.
If you just go back a slide, because so that slide there, this explains the 400-foot rule. So what that slide is saying is, if you take a body of air that's being heated up to 25 degrees on the ground, and the Met Office tells you that the air on the ground, its dew point is 15 degrees. In other words, if you take the body of air on the ground and cool it to 15 degrees, it will condense in a cloud.
Right, so it's 10 degrees different.
There's 10 degrees difference. Right.
4,000.
So what you have is that body of air that's being heated up by the sun is at 25 degrees, it starts rising and losing temperature at 3 degrees every 1,000 feet. Now, the dew point also loses temperature as it rises. It gets lower, but slower, 5 degrees, 0.5 degrees per 1,000. So those 2 points, they move up. The dew point is losing heat slower. The hot air is losing heat faster. Eventually, they meet at a point in the air And that's your dew point. That's when that body of air will condense out into cloud.
Yes, so 25 degrees, yeah, so that 25 degrees gone to 13 and over 4,000 feet, it's lost
Yeah.
0.5, which, you know, 0.5 of 1,000, which is that's 4 up there. So it's lost 2.
Yeah. So if you work it out, the net then is 2.5 degrees per 1,000 feet, which is your 400 foot per degree difference between your actual body of air, which is 25 degrees, and the dew point on the ground. So then on this particular slide, what it's showing is that the environment lapse rate is also showing there. It's saying that on the ground, the body of air is roughly 20 degrees. There'll be pockets of air that might be heated up to 25. The body of air is 20. It's also cooling down as it rises 2 degrees. That body of air that at 25 degrees, that bubble of air, never hits the dew, never hits the ELR. It condenses out into cloud. That act of condensing into cloud releases another little bit of heat. And it just keeps on rising. So that cloud there has no reason to stop rising. There's nothing that's going to stop that cloud rising right now on that graph.
So
It was last seen in orbit.
Sorry, Ben, you lost on that last paragraph, that last bit. I got the bit about the environmental lapse rate.
Yeah.
Because the environmental lapse rate, as it hits that point,
Yeah.
The
The environmental lapse rate is just a standard.
and that's not that's not going to form a cloud.
No, the environmental lapse rate is just something you measure against. It's a standard, it's an average.
Yeah.
The actualities on the day is you've got your dew point and you've got your body of air, which is your bubble of air, which is 25 degrees.
But I'm a bit confused because hot air rises, but then you're saying that so that so the cloud, I think hot air. So the air in the cloud is still slightly, it's less cold, everyone put it, or hotter than the environmental air. Because of that, it's then rising because the environment it's in is cooling less slowly than it is itself. So therefore, it's still going to go until it actually equates. Until it actually equates. And it's not equating.
There's no reason for the air to stop rising if it's always hotter than the year round.
Because it's natural.
So that chart right there, there's nothing to stop that cloud getting bigger and bigger and bigger, other than the fact that it's not being fed by water vapor, but the air, just in that chart. Now the ELR there is a theoretical.
It's
average.
idealized.
It is, yeah. The next chart is going to show you the actual air temperature, which is the black line. This is the actual temperature of the air. As you can see, it's not the ELR. It's all over the place.
Right, so because the actual air temperature then at that point increases at the cloud top, therefore the air in the cloud then is capped.
So it can't go any higher.
Because hot air can't go higher.
Because it's not the same temperature as year round, so there's nothing to make it go higher.
The only reason you might see it go higher than this 6,000 foot top is just because it's got inertia. It might poke its head above it, but it have to go back down.
Why does the environmental air increase as it goes higher again?
Several reasons. So this, let's say, inversion down here, we can assume that that's been the overnight inversion. So what's happened is that if there's been a little bit of a clear sky, the ground's just radiated its heat into space, and the air next to it has actually cooled down past what the air at height is. Now, up here at the 6,000-7,000 foot height, maybe you've got a little bit of a high pressure. That high pressure is causing air to descend through the atmosphere. And just as air rises through the atmosphere and becomes less dense, becomes less hot, as you push it down through the atmosphere, it increases in temperature. And that's generally the cause of inversions at height. is upper atmosphere movements of air down.
Bit like a pump, pumping through my pump feels hot.
Yeah, yeah. There are, there are other reasons as well. Heating a layer of cloud.
That video
Could well be one.
you circulated, that link, I think
Yeah.
that actually went into some of the reasons. There was at least one more cause for inversions, I think.
I mean, the big inversion at the top, the tropopause and up into the atmosphere, the stratosphere, where temperature increases with height. That's caused by the sun heating that layer of the atmosphere, and that being the ozone layer and taking out the ultraviolet rays. Well, that all gets transformed into heat.
This is a simplified skew-t, really, is what we're looking at there. So if you compare that to the last slide you can see a very definite inversion on the actual air temperature, which caps the side at the top of the cloud. Right? If you just go back, the actual air temperature, right, actually gets hotter from 5,000 feet to 7,000 feet. The body, the whole massive area here, it doesn't. So there's nothing to stop that cloud being vertically growing vertically. There's no cap on it.
And don't forget here at 10,000 foot, it's 700 millibars. There's a good almost third less atmospheric pressure. So there's plenty of difference in buoyancy that's possible with big pressure changes like a third of atmospheric pressure. So just summing up those different slopes of the adiabats, again, you've got this difference of the the rising rate of a moist adiabat versus a dry adiabat, giving you unstable conditions here when you're below the dry adiabatic to absolutely stable when you're in lapse rates that are above the moist adiabat or the saturated adiabat. Again, I'm not entirely sure that I've seen a question on that.
No, I don't think they asked about condition state or condition unstable.
This is very much a question on the exam. You will get a skew-t. So what we're looking at here are actual forecasting diagrams that are a more complex version of the previous slide. So the big difference is that the temperature, rather than being on the x-axis and representing a vertical component, the temperature actually is this solid line here, these isotherms here. So this is the freezing level, the zero isotherm. And then we get some sense of height with these isobars. So these are the 200 millibar, and then from what we had before, 700 millibar, we can take that as being 3,000 meters, 10,000 feet. And then 9 and 800 millibar being 1,000 and 2,000 meters. So this is really what we care about, everything below 700 millibar. Unless we want to see what cloud building capability there is with air being lofted way higher, all the way up to the tropopause. So We've got other features of this graph before we come to what's actually plotted on this graph. We've got wind at height. Are we clear on what these wind arrows actually indicate?
There's direction and strength. I don't understand how to do strength.
Sure. So the direction is westerly going to southwesterly. We know that because these are arrows and you can see the feathers on the arrow are at the back. So they're all shooting that way or shooting that way. For every 5 knots, you have a half a bar, and for a 10 knot, you have a full bar.
Oh, okay.
So you can see here that this southwesterly is at 30 knots. Triangles, 50. So right at the top, we've got 65 knots. We've got a bunch of other lines on this graph. And because we've skewed the temperature, we can actually make it much more shortened horizontally. So things appear more vertical. It looks a bit more like the atmosphere would, we would expect it to look, I guess. So we've made these lines stand up, but all of the other lines are fairly skewed along with the temperature. So we have here two lines, B and C. So you can see B and C have different rates associated with them. C is steeper because it's only 1.5 degrees C per 1,000 feet, 3 degrees C per 1,000 feet for the dry adiabats. This is just one highlighted here. You can see dry adiabats all the way through and saturated adiabats all the way through, although fewer of them. What you've also got are dotted lines going this way. Now, these are not isotherms. These are effectively your mixing ratio. Mixing ratio is just another way of saying, how is my dew point changing with height? Okay. And you can see here that we get a line that equates to 0.5 degrees C per 1,000 foot. And then we come to the actual data. So on this, from a radiosonde balloon that's been lofted up, we get some figures that come down. We get pressure radioed down, we get the temperature radioed down, and we get the dew point or the relative humidity radioed down, from which we compute the dew point. And there might be, I don't know, hundreds of data points that get radioed down as the radio balloon goes up. And we get this trace here.
Is that saying that the dew point is 20 degrees?
So the dew point is actually relatively close to the
19,
lapse rate of the day. Yeah.
But 19 degrees, so the water will be on the ground at 19 degrees. It's quite high, isn't it?
Well, yeah, I mean, if you took a plastic bag of air, shoved it in the fridge for 2 minutes, it probably would form a cloud very quickly on that day at that height. But if you then went 1,500 meters in the air and got that same plastic bag of air and then put it in a fridge at that height, it'd probably take 1/4 hour to form a cloud. But it would form a cloud because the fridge would take it down to 4 Celsius, which is below the dew point. And then again, we get a feature here, maybe it's 12,000 foot to 14,000 feet, maybe, where the dew point is relatively close to the lapse rate for the day. And that means that the air is actually, relatively open to forming cloud at that height. It wouldn't take a lot of disturbance, so you may well see lenticulars at this kind of height. But what we're interested in this diagram for is to tell us what changes in temperature, particularly what changes in temperature at the surface, are going to do to the parcels of air in contact with the surface. So as we take this line here, then you can see here there's a little bit of a ground inversion, stopping at maybe 1,200 meters or so. I don't know where this is from. We might be in the mountains somewhere, but this might be an inversion from the day of katabatic flows coming down the mountain at night, leaving cold air in the valley bottom, and radiative cooling overnight, giving us quite a relatively high inversion. On this day, you might want to be taking off above this inversion. You might want a 2,000 meter high takeoff. But what's going to happen as the sun warms the ground during the day is that we're going to get some temperature rises. And as you see down here, down at the ground, going from 20 even to 30, and then going up at the the dry adiabatic lapse rate, you're going to need some big temperature differences right on the ground in order to get past this inversion. So reasonably inverted day, but once I think you can take off at 2,000 meters, it wouldn't take too much warming to give you. So I'm just taking the height from here.
Okay.
Yeah, roughly
Yeah.
1,000 millibars is sea level, 900s, 1,000 meters, 800s to 700s.
But you have to calculate cloud base first because you've got the transition between dry and saturated.
Yes, yeah. So, maybe if we did take off at, let's say 15, let's take off at this 1,500 meters here. We're going to go in here and we're going to say, it's midday. We've got 5 Celsius that the air is heated up by. So it's going to go up by, certainly, I make it to at least 2,500 meters. Probably 3,000 meters, 10,000 foot. But we're crossing these dew point lines along the way. So the point at which, I need some kind of straight line. Here we go. The point at which our dry adiabat of our heated parcel of air reaches an isotherm, a mixing ratio line or something projected from the dew point. I think we're going to be in cloud fairly quickly there, because that's maybe there, just short of, I guess, just above 2,000 meters. Does that look right? Mm-hmm. So we're only going to have, if we're taking off at 1,500 meters or so, 500 meters before we hit cloud base. That's probably a little bit more than I wanted to go into on that particular skew-t log chart. I wanted to show you just the features of the chart itself. But that's how you use a skew-t.
On a better day, then the dotted lines, the mixing ratios would be a lot further apart.
No, so everything you see in grey is set. That is the features of the chart that you're looking at. Ignore these, the isotherm, the isobar, and these purple, dotted green, and full green lines, because they're just highlighting the trend lines for what is on every skew-t chart. It's the lapse rate for the day, the temperature of the air with height, and the dew point for the day. That's what changes. That's the data we're looking at. That's the data that changes from day to day, from hour to hour as well. So to get a great soaring day out of today, you would want this dew point line to be, you would want the dew point line to be down here.
Yeah, the two lines that change is just the red and the green.
Yeah.
Everything else is just a grid to help you plot your bits and pieces.
Okay.
That's all. It's like when you're doing.
I get that. I'll have to go through it at the end to save people online.
So the video that Pete circulated is really good, actually.
Hmm.
The one piece of information we don't actually have is how warm that thermal actually is at its base. Because we kind of, draw a line that we think it might start from. You might try a few, to see what, because we don't actually know what that's going to be. It's going to be a warm parcel of air, but how much?
So this is a real one from today, actually. And you can see how, we've had quite a bit of cloud at mid-height with the dew point and the temperature trace for the day being so close to each other. And we obviously, we had a clear night overnight. We've got a tiny little inversion down at the bottom there, very close to the ground. And then you see why we got some of the rain that we did today. Because the dry adiabat, is going way high. So you get a, 5 Celsius change, 5 Celsius change in air goes up to 850, 800, 2,000 meters. But 7 Celsius would take you beyond 10,000 meters. Hence, I had to bring the washing in today. Any more questions on skew-ts?
You need to study them. You're not going to learn them in a presentation like this. There's a huge amount of information on skew-t. You sit down, look at it, go through articles, work it out yourself.
That video I circulated is good. Kelly Farina does interpreting skew-ts for the common man as well. I find that helpful as well. So, just to sort of sum a bunch of that we've gone through together. Clouds, temperature, moisture, relative humidity. As we've seen, it's relatively linear, this drop in relative humidity. When we look at it in terms of the dew point changing at 0.5 degrees C per 1,000 foot. But imprinted on that is the humidity of the atmosphere based on what it's passed over before, the temperature now, the temperature at different heights. And that massively affects the humidity of the atmosphere at all of those different heights. And therefore its propensity to form cloud at all or at different heights. And sometimes I'm just sort of gobsmacked that we actually just get so much variance from completely blue days to completely cloud at all levels and in between days. And it's neither one nor the other, because some of these parameters are sort of relatively finely balanced, and they also, they're all correct for each other. But we could equally be easily a Venus where you never see the sun, or we could be a Mars where you occasionally get some cirrus, and that's it.
Or in the middle of Sahara where they don't have a huge amount of variety either.
Yeah.
It's just to do with the latitude we're at and where we're at in the world. We're pretty
So
much
what's
set
going
between
on?
the two big
Yes,
air masses.
yes,
The Arctic
yes.
mass and the Arctic air mass are all kind of doing this, and we're the meat. That's where the weather's at.
There you go. We're privileged. We see it all.
Well, I said
An island as well.
We're at the battlefront. Yeah.
So just on the second point, where you've got a dew point, you've got condensation that needs to occur. It doesn't always definitely occur if the atmosphere is particularly clean. If there are no nucleation points, so it's really helpful to have nucleation points for water to condense around. So that's why you get quite a bit of low cloud near the sea quite often, because there's salt crystals. So think of the fogs rolling in northern Australia or on the Atlantic coast in northern USA. For us, we've got plenty of nucleation points. We've got both salt, dust,
Is that
pollen.
what causes sea frets? Sea frets.
Sea frets, I don't know. I don't know.
It's basically fog coming off the sea.
We've heard that term.
There's salt in the air and what have you, and that's can create.
So the salt,
water drop.
the salt's going to help, but generally, if you've got descending air, it's warm air, and then it comes into contact with cold surface.
Yes.
That is just acting like condensation on a window
Yes.
with cold air outside of it.
Yeah.
So this relative humidity I've been banging on about for a long time is just a simple ratio. It's the amount of water vapor in the air versus the amount of water vapor that particular parcel of air can actually hold. And you measure that in grams per kilogram. And it can be quite high, it could be 80 grams per kilogram, but it could be quite low. And in fact, above the tropopauls, the relative humidity drops pretty much to zero.
Is it warm air generally holds more than cold air?
Yeah.
It can hold more.
Can hold.
It does hold more. That was physics.
Well, it has the capacity to hold more. But for instance, if you have warm air that's come across the continent, it'll be extremely dry. So it'll be a very dry air mass. It has the potential to hold more water if it flows over a water source.
Yes.
So if you have a big body of air coming up across the continent, it's going to be very dry. There's no air on the land. There's no water in the land for it to pick up.
Yeah.
If you have the same body of air coming up from the southwest over the ocean,
Mm-hmm.
it'd be warm and a lot of water because it's picked up all that water.
If you took, but basically if you take the warm parts of air and cool it, then it will essentially start to condense. I mean, that's partly why you get the fronts. You get the mixing of air at the fronts. Basically, the mixing causes the warm air holding more moisture to cool and deposit precipitate.
And then just to give us our different types of cloud, we've got the freezing isotherm, the 0 point, and anything that's condensing out of there is likely to form diamond dust, hail, snow, general ice crystals, sometimes little spicules, lovely things. So on to clouds themselves and the formation of clouds. Now, it's not just convective clouds. Convection meaning air uplifted.
Yes.
And convection often occurs because of temperature differences, giving rise to buoyant, less dense air. It doesn't matter how air rises, just that it rises to form cloud.
Yes. You could take it up in your bag, you see, like instead of going to your fridge with your bag, you could go up in your paraglider and have a cloud in your bag.
Yeah.
That height.
So,
Cloud catching, cloud hunting.
So equally, where you've got a mountain range in a way, or an individual mountain orographic left is
pushed up the hillside.
Pushed up the hillside. Thank you very much. Yeah. Cloud formed by turbulence and mixing. So we would see that when we're landing in a plane, it's got the flaps out. You're coming into Ringway Airport, flaps down, and you just see that huge vortex of water vapor coming off the back of the flaps, which is cloud formed by turbulence mixing.
That's wind on the ground, turbulence from the ground.
No, it's turbulence. It's that vortex with the low pressure inside it. But turbulence and mixing,
in the atmosphere.
Turbulence and mixing in the atmosphere could be wave downstream of a mountain range. Could also be temperature stratified air, so cold air and then warm air on top of it.
Yes.
But as you move over a rough terrain, that actually then goes and forms fog as the warmer air from above comes into contact with the cooler land, or more commonly the sea below.
Yes.
But that mixing, that turbulence would be potentially lenticular, like I said. Cloud formed by widespread lifting. So our occluded front. Wave, again, I guess a special case of turbulence. And then fog. So because we're close to the ground, we get a lot of effects. Radiation fog, where the ground has radiated away its heat overnight and takes that air in contact with it below the point at which it can actually hold water vapor and it condenses.
Yeah, so sometimes you've seen the weather forecast and it's gone fog, mist, fog, mist, fog, mist. Right. Well, so what's the difference between fog and mist?
Your visibility.
Yeah.
So I think, fog is anything below kilometre. Yeah. And then the sea, hill fog, advection fog, as well as different subtypes. But effectively, you're coming into contact with cold surfaces, but not due to necessarily radiation. Your sea is cold simply because it has a bigger specific heat capacity. It takes a lot more energy to heat it up. There we go. Nice demonstration of orographic there. Orographic again. Looks like, where's that? Looks very nice. And then perhaps interesting flying conditions, cumulus castellanus. But it's interesting that, on a day where you have a convective depth in the cloud, that you can see as a relatively consistent height here. You get these big beasts that punch through. And so cumulus castellanus could be just the first thermals that were just starting to get strong enough to punch through temperature increase with height, an inversion for the day. But just, just as easily, they could be the formation of cumulonimbus as well. And of course, you could just be having the cumulus castellanus where you've actually just got the best sources on the ground. And then wave lenticulars, yeah. Effectively, the cloud stays still and the air moves into it, condenses at the top of the wave, moves out of it and reabsorbs that moisture. So these clouds generally are always regenerating themselves. They do rely on the wind at height being a particular sort of speed. So 15, so certainly need a bit of speed with wind at height, 15 or more knots. And quite often they will be on top of a mountain range, but also survive wavelengths down from a mountain range. And I mean, just out of interest, no test on this, the reason that they survive down range of a mountain range is that once this sine wave in the atmosphere sets up, they bounce between two layers in the atmosphere. So, typically bounce between an inversion at the top and the bottom would give you a very stable set of lenticulars that go for many wavelengths downwind.
So would that make good flying conditions?
Wave on the hill, yeah.
Yeah, if they're held in by an inversion, say at 6,000 feet.
Generally, paragliders can be risky because the wind strengths are strong.
Yes.
And the wave can move around, so you can very quickly go from being in the lift and it being very smooth and you're going up and up to finding you're now in the cycle of the wave where you actually need quite a bit of turbulence.
Yeah.
Sailplanes love wave.
Yeah.
But sailplanes can keep up with it. And they'll surf those wave fronts and they can go up to all sorts of heights.
The really turbulent stuff is the rotor cloud.
Yes.
Right,
Yes.
usually under.
Yes.
So yeah, but on a paraglider, wave, when you do contact it, can be brilliant. And,
It's disturbing, really. It's just going up. Everywhere is going up.
Yeah.
You know that, don't you?
Yeah,
With about being sick of wave and weather.
there's a certain video.
It's just going up everywhere, going up. You just can't get down.
It's not that bad unless the cloud starts moving around you.
Yeah.
It can do that,
But of course, for the front of the wave, which is all lifting, if you're going to go cross country, you've got to go through the back of the wave, which is sinking. And that can see. I've been on the ground very, very quickly on a cross country flight. In 3 or 4 meters of sink that you just can't really escape from.
Did I hear that Richard Meek had managed to successfully dolphin backwards? So that wave, because it's bouncing, you might take off on the hill here. You might have, obviously, sorry if you're online. But basically, you might take off on one hill and climb its wave, and then you can theoretically jump downwind to another wave path.
Yeah.
And find another ascending path.
Yeah. So I mean, hang gliders certainly talk of doing that and have done that quite a bit, but they've got much more speed range to get through the sink.
Did Richard do that, or did he?
I'm not sure.
I heard it. I'm not sure.
Well, we can ask him on Thursday.
Thursday, yeah.
We have two types of airflow, turbulence and mixing. Why could that possibly be important?
Oh, if you go back, I'll explain.
Oh no, I was going to explain.
Oh, sorry. I'm sorry, I thought you were going to go, what's that slide there for? Sorry.
So, you know, the reason to move onto this particular visualization of turbulence, you know, if you imagine you've got wonderful laminar flow coming into the first of these row of turbines, and then you've got increasing turbulence that spreads out downflow after them. You know, you've got a safety concern there, in that we at some point have got to land, or we've got to fly in the lee of the wind with some obstacle, and being downwind of that obstacle can give us pause for thought for what the turbulence is going to give us as we get near either an obstacle or the lee side of a piece of ground that we're flying next to.
But for practical example, seed field.
Eden Field. Okay. Well noted.
What's Eden Field?
It's a hill near Bolton and Bury, they say. If you come down M66 from Blackburn, you'll get to it. And
They don't have a football club anymore.
does he not?
Yeah, they did it a few years ago. Yeah,
It's gone.
they're gone. Yeah.
Okay. Anyway, there's wind turbines at Eden Field.
All right.
Right behind takeoff. I mean, yeah, it's far enough. But
You know they're there.
So clouds, you know, I guess you know most of them already, but cumulus, heaped, stratus, flat, nimbo, raining, alto, cirro, mid-level, high level. You'll need to know roughly the right sort of heights. But mid-level clouds, you know, maybe 8,000 feet, high-level clouds, 15,000 feet or more. And then just for personal interest, you know, it's nice to know some of the different types of cloud. So this cirrus here is mare's tail, often quite associated with the jet stream itself, actually. And then maybe dappled cirrocumulus. That cirrocumulus joins up into lines, that can give you this macrod sky. No questions there? Rain. What can I tell 5 or 6 people from Yorkshire about rain that they don't already know? One thing that will be on the exam is when in the year maybe you're looking at a synoptic chart, or when in the year you're looking at a skew-t diagram, and that might be part of a question that you need to bear in mind. So, you know, Steve, particularly with your, there could be a couple of answers that are right for a particular question. Well, you know, maybe think about the time of year for the bit of weather that you're interpreting. Because anticyclones in the summer and the winter, they're a little different. You know, very often with a low pressure, they're actually the same, but warmer and colder, wetter and less wet. But anticyclones can be, you know, quite cloudless. For winter, those really, you know, beautiful, crisp winter cold days. Big temperature drop at night time. Whereas in summer, that, you know, if you get a bit of moisture or if you've got quite a bit of pollution in the air, they can be really quite hazy, can summer anticyclones, and that can block quite a bit of sun getting down to the ground in a particularly, you know, sort of deep example. And then just a summary of the different types of conditions that we've been talking about. High pressure air, sinking, easy to visualize, it's being pressed down from on high. Low pressure air, just think of your Hoover nozzle again. God's Hoover nozzle. Stable and generally mild conditions versus windy and unsettled and wet conditions.
You've obviously got a lot of sea experience. I mean, what would you say most of your flights have been in low or high pressure though?
Certainly higher pressure than 1013. Yeah, generally higher pressure than the standard sea level for the UK. Yeah.
It's kind of paradoxical.
Yeah. But, you know, generally the classic XC conditions that we get in the north, you know, you're clearing a low pressure out, so you're going back up through the isobars. So day one or day two after a cold front has come through, give you your blue sky, puffy little clouds, soaring conditions. Maybe that's associated quite often with, you know, with an arm of high pressure coming through before the next springtime low comes through. And then, you know, high pressure conditions, you know, a couple of easterly flights and northeasterly flights that have been almost cloudless, yeah, so getting out onto the Fylde coast, having left the Forest of Bowland, that was the last of the cloud. And there was nothing in the atmosphere able to get above the day's inversion all the way to Blackpool that day on that northeasterly flight.
That was April, May, was it?
I think it was May, yeah. Yeah. And then, again, concentrating down, now we've had a little summation, concentrating down on the smaller features, anabatic and katabatic, and maybe you get a bit of this in Scotland, Wales and the Lake District, less so for us, but certainly very, very important in mountain conditions in the Alps. So much so that katabatic flow might actually start on the easterly slopes of mountain ranges during daylight. And you will not find lift for love nor money on the east side of a mountain slope in late afternoon. But yeah, anabatic during the day as air rises. Don't forget, as air is rising, you know, it's buoyant, but it's still in touch with the ground that it wants to rise up the slopes of. So sometimes, you know, that will lead it to be going up the mountain slope quite persistently until it reaches the top or an over-steepening minor peak. And then valley centre lift during the early evening. Sometimes that translates as magic lift in the Dales, but you'd find that maybe over trees, forests that have been heating during the day. as the land starts to cool. But what takes over from those anabatic winds, or what feeds those anabatic winds during the day, gives you valley winds. And it's pretty important to be aware of what valley winds are going to be doing in any mountainous area. So the Lake Districts, yes, North Wales for sure. The Dales, I don't really encounter that kind of thing much. The Alps, for sure. So the valley wind, it wouldn't be impossible for you to be landing backwards at 3 in the afternoon if you were in the wrong valley. So local knowledge, yes, please. If you're arriving somewhere that you're not familiar with, or if you're on a long cross country in the Alps and you need a bit of a steer as to which valley is going to have which flow in it, always think about where is the nearest biggest mountain, because pretty much every valley will be flowing in a direction towards that mountain, or towards a valley that flows towards that mountain.
If you go to somewhere like Annecy, you can actually get a map that has all the valley winds marked on it. And those valley winds will always be the same, irrespective of what the geostrophic wind is doing.
Right.
So it's always dependent on the terrain.
Even if it's the opposite direction.
Oh, absolutely, yeah, for sure. Yeah. And so, you do need to be aware of the winds that you're flying with in big mountains. And part of the reason is these valley flows. And part of the reason is that even when you've escaped the valley flow, if you're, for example, flying in a 15-kilometre-an-hour westerly wind, which is, it's not heinous, it wouldn't be much here in the Dales, but you set off in the morning, so you're flying those southeasterly slopes, and you get a good, nice strong thermal, you're going to pop up on the lee side into 15 kilometres an hour of wind, it having just come over some spiky, sharp rocks.
Is that the geostrophic?
So you're going to know about that, yeah.
Is that dynamic lift or the geostrophic wind blowing over the tops of the hills?
So yeah, if you've got a westerly geostrophic wind, you've got a westerly wind flow from the pressure system, but you're flying the morning ridge southeasterly, you get a good piece of lift and you come above the hillside, suddenly your nice, calm lee side thermal is going to be bent over and it's going to have a lot of mixing with 15 kilometres an hour of air.
Do you guys understand this? How a valley wind sets in?
It heats up and then cools down. So the air is during the day, the land either side of the on the hills is heating up, so therefore it's rising, it's sucking in the air, going up the valley.
Yeah, that's it.
Yeah.
Valley systems add to each other.
And that's sinking air, but that sinking air is then displacing the hotter air that would have been or was in the valley and pushing up into the air.
Sometimes. Yeah.
In theory.
Sometimes, not those, and it's just lovely and magic lift.
Yeah.
I was in France, and where I was recently, where I was staying was quite a narrow valley, and there was a castle on a hill with a flag, and I used to watch that flag, and every single day, up to about 11, 12, the flag would be just there, and then it would start flying, and this valley wind would set in, and I go, oh, bad, it's in the air. And it would be blown up the valley every single day from about 12 through to about 4, it would be blown really strong. And then it would drop. Every single day like clockwork. It was amazing to see. Yeah.
Exercise time.
Since it's a building island, isn't there? So you can sort of-
Yeah, there isn't any big enough hills in Ireland. No.
There's a lot of lupus, isn't
Yeah, you have other things to worry about there. South Valley winds.
Okay, quick shout out.
Oh, God.
Stable, unstable. What does that mean?
Difference, well, it's the differences between the environmental lapse rate and the,
Simpler than that.
yeah, okay,
Will a parcel of air rise or not if it's heated?
right, okay.
Inversion.
It's,
Hot air above cold air.
warm air cooling, warm air coming down.
Not necessarily.
Yeah.
Inversion.
It's hot, a layer of hot air above cool air.
Yes. Temperature rise with height. Isothermal. Or an isotherm.
Oh, that was on the thing, that was on the skew chart.
Yep.
Uh,
ISO.
uh,
Equal. Line of equal temperature.
right,
Adiabatic.
It's
that
air
is,
going up.
Air going up.
Yeah.
It's the process of pressure drop,
Yeah.
temperature drop with air going up.
Yeah.
Diabatic.
Air going down.
Right, yes. Sorry, adiabatic.
Though I don't even know why I put those in there.
Yeah.
Adiabatic, I think.
Diabatic is the process of temperature drop and pressure drop with air going up.
Don't think you have to worry about those two.
Yeah. I think adiabatic cooling is cooling next to cold surfaces.
No, it's where there's neither anything added or taken from the parcel of air to the planet. So it's losing its temperature by itself. You're not adding anything into it or taking anything.
It's not affected by the outs.
Yeah.
The temperature.
Yeah, like a thermal tends to be
Yes.
adiabatic because
It's almost like a balloon going up. It's got its little, little world of temperature sustained in it, which might be affected.
Yeah.
Yes.
Katabatic.
That's air going up the side of it's
no,
down.
Anabatic.
That's
air going up the side.
up the side of the
Goldfram.
Well,
Complex.
It is, yes.
it's front of cold air. Yeah, it's front of cold air.
Yeah.
That's the best way to,
And warm,
So
warm front.
warm air.
front of warm
Over.
air. Well,
Cool sector.
yeah, or
Yeah.
Behind a warm, behind a warm sector.
Yeah.
Okay, what's shown on a synoptic chart?
High pressure, low pressure systems.
Isobar.
Isobars.
Distance in pressure.
Equal, well, ISO need equal.
Yeah.
Equal amounts of pressure.
Okay. Low cyclone.
Depression,
High anticyclone.
high pressure.
Occlusion.
A mixture of
Cold and
cold and warm.
Difference between veering and backing.
Veering is clockwise,
Clockwise,
backing is
backing.
anti-clockwise change.
ELR,
Environmental lapse rate.
which exists where?
In the accident.
But kind of it's sort of idealised.
Yes.
DALR,
Dry
Dry.
adiabatic lapse rate.
SAS.
Saturated.
Saturated.
That's right.
What's a ICAO standard pressure? What's the pressure setting?
What, standard pressure?
Yeah, this is in air law and theory of flight as well.
Do you mean like mean sea level?
UNH
You mean 101?
213.2.
Good. Dew point.
The 100% humidity.
Okay. Relative humidity. It's a ratio of what?
Ratio.
How much moisture there is in the air,
Compared to
the environment around?
how much moisture it could hold.
All right.
So it's a percentage. So if it's 70% humid, that's its relative humidity. There's another 30% it could hold. Troposphere, tropopause.
Troposphere is what we're-
Yeah.
Tropopause is the space between us and the stratosphere.
Boundary layer.
Between the two.
No, the boundary layer is what we're in as well.
Yeah,
The boundary layer,
the bottom 10,000.
yeah. Generally, it's what will vertically mix in any given day. Some links, I think we'll add more to the skew-t. We'll add some videos to that before I send this out. So, Meteo is one of the bigger ones, along with flight theory and air walk.
And what are the big ones? Yeah. I like
It's one of the big three.
I like what you've done there.
Did you get through those three? You're okay.
Yeah. Unfortunately, there's no points for writing your name on the exam.
Not even in French.
Not even in French.
To be fair, it's been done already, not by me. That's how they come out.
So there's
Okay.
couple of things.
Any final questions?
Yeah, how much would it cost you to take an example?
Couple of things for just your exam technique, which I think you find useful, is one, read the question. Two, some of the questions aren't phrased as well as they could be, but the BHPA are not trying to catch you out. So if the question isn't fully understandable, it's not because they're trying to trick you, it's just they didn't phrase it so well. So keep that in mind. There isn't a trick that you have to figure out. How did they find that? It's not phrased well. The other one is most of them are multi-choice with 4 answers, and generally you can very quickly discount 2. So rather than trying to pick the right answer, if you're not sure, sometimes you know the right answer, just pick it and move on. If you're not sure, discount 2. You'll generally be able to discount 2, and there'll be 2 left. So if you're unsure, there's 2 approaches you can take rather than guessing. Leave it and move on, because sometimes the answer is in the next question or the question after actually gives you the answer for that. If that doesn't work, pick the choice that is most safety related.
Yeah.
Because that's
Simple
the one
and
they
simple.
want you to know. So, like, I don't know, if the question is, what kind of clouds could you get in these conditions? One says, and you can, it could be cumulonimbus, or it could be nimbus stratus. And if you're unsure which one it is, the chances are it's cumulonimbus, because they want you to be aware of cumulonimbus and not cumulonimbus. Now that's just an example. So if you can't figure out what the answer is, go for the safest option, the one that indicates the safest approach, and that would be your best guess.